Dominic, and I'm presenting the Group 2 alkaline earth metals with Shauna and Logan. So we're going to be talking about beryllium, magnesium, calcium, strontium, barium, and radium. To start off, I want to talk about some of the elemental trends of the Group 2 metals. You probably remember most of these from Gen Chem or other chem classes you've taken, but we have electronegativity, which is an atom's tendency to attract an electron. We have ionization energy, which is the energy required to strip an electron from an atom. Electron affinity, which is the energy released when a neutral atom accepts an electron, and then we have atomic radius, which is simply the size of the atom. So electronegativity decreases down the group. Ionization energy and electron affinity also both decrease down the group, and the atomic radius will increase down the group. It's important to note that these trends are just general, and there are, of course, exceptions to this. So, for example, the ionization energy of radium is actually slightly higher than barium, making that one of the exceptions. Next, I'd like to talk about some of the basic chemical properties of the group 2 elements. So, in general, they lose 2 electrons to become a +2 charged cation. They are good reducing agents, and their reduction ability will increase with their atomic number. They are reactive with acids. They are good conductors. They are malleable and ductile, and they are reactive, meaning that they are not isolated, found in nature. And on the right, I just have a few examples of some interesting facts and uses for some of these metals. So magnesium, as you probably remember from organic chemistry, can be used as a Grignard reagent, having the form of R magnesium X, where X is a halide, and the magnesium is binding the R group to the halide. Calcium is used in something called Portland cement, which is a mixture of calcium, silicates, aluminates, and ferrates, and it's produced on the scale of 10 to the 12 kilograms annually. And water and hydroxide will link these components into strong crystals, so it's a very common and useful material. And strontium and barium are actually used as halide salts for fireworks, and they exist in nature as oxides. And radium it was first discovered from uranium ore in 1898 by the Curies, and it's radioactive. So radium is actually what uranium will decompose into, and radium has a half-life of about 1600 years.
So let's take a look at the chemical reactions that are relevant to the alkali earth metals. Some of these include oxidation, halogen reactions, reactions with water, precipitation reactions, and acid-base reactions. So first up, we'll take a look at oxidation reactions. So as you can see on the right-hand side of the slide, there is the magnesium ribbon experiment, which is the combustion of magnesium, and it creates a very, very bright white light. However, the other elements in the group do not do that, so calcium and beryllium combustion are much more tame, but this property of oxidation makes these metals very valuable for fireworks. So as strontium, barium, and magnesium all produce very vibrant colors. Next up, let's take a look at halogen reactions. So the halogen salts that beryllium forms are very toxic to humans, and that's why they are not bolded. However, magnesium chloride and magnesium iodine can be used as health supplements. Calcium chloride is used to prevent ice from forming whenever it gets cold outside. Strontium chloride is pictured in the white substance below and is used to strengthen teeth. Barium fluoride is interesting because it has a very low index of refraction, and radium fluoride fluoresces, as seen to the right. Moving forward, let's take a look at how the group 2 elements react with water. So interestingly enough, beryllium does not react with water. This is because it has a small atomic radius and holds that valence electron in very tight. However, radium, the valence electron experiences a very low effective nuclear charge, so it rapidly and violently reacts with water. Similarly, anion precipitation can be predicted with periodic trends. So with the hydroxide ion, magnesium is the least soluble, while barium hydroxide is the most soluble. However, the opposite occurs whenever it's reacting with a sulfate or carbonate ion. So barium is the least soluble, while magnesium sulfate is the most soluble. And this is due to the different shape of the molecule whenever it's a 2+ charge, so it's in a 1-to-1 ratio, versus in a 2-to-1 ratio with the ion. To ground us a little bit, let's take a look at some specific acid-base reactions. So acidified beryllium chloride with hydrochloric acid can be used to test for sulfate ions through the precipitation reaction previously discussed. Magnesium is used in an acid tablets as magnesium hydroxide reacting with hydrochloric acid to produce a neutral salt. Calcium carbonate, or otherwise known as limestone, deteriorates in acid rain, so the sulfate ion exchanges in like a Lewis acid-base relationship. Strontium hydroxide, in accordance with periodic trends, is weaker base than the other metals, and barium acetate is used in organic synthesis and textiles.
Okay, so how do the group 2 elements relate to the rest of the periodic table? So first, if we think about periodic trends, in comparison to the normal earth metals, these group 2 elements are going to have obviously a higher nuclear charge, and so their electron shell is smaller, they're more compact, and they're denser. What that means is that they have higher ionization energies as a result of the greater nuclear charge holding onto those electrons tighter. They also have higher boiling points and higher enthalpies of fusion and vaporization. Another really interesting thing, particularly about beryllium, is that it's really commonly used for alloys. In particular, beryllium copper, or BeCu alloy, is pretty important in situations where you don't want any kind of spark or flame. It's also, because it's non-ferromagnetic, it can be used to service machines like MRIs or NMRs that otherwise, if you took steel tools in there, would cause problems. Finally, as you've probably seen already, these elements have high affinity for halogens and oxygen. They like to form halide salts and also oxides. And so the next thing is, how is group 2 biologically relevant? So the two major contributors to group 2's biological relevance are calcium and magnesium. Magnesium is a really important ion, magnesium 2+, in protein kinases. They help do what's called phosphoryl transfer. This on the left here is 3 different structures of protein kinases that have magnesium as a part of their active site. So this left one has 2 magnesiums, this one has 1, and this one actually doesn't have any. The thing on the right is what's called an EF binding domain, and this actually chelates calcium 2+. It has use cases in a lot of different situations, but one is in an EF2 kinase protein, which actually stops what is the EF2 protein from facilitating RNA translation in the ribosome. Just as a side note, calcium 2+ is crucial in photosynthesis, but I thought these were more interesting structures. And speaking of interesting, we're going to talk about beryllium a little bit. I should have mentioned just a moment ago that beryllium, strontium, and barium are all pretty toxic, and they don't feature a lot in biology, but beryllium has a lot of interesting properties. One thing that just recently happened is they were able to synthesize this compound called diberyllicene, and the structure is shown right here. This is actually an analog of it. It's not the exact same, but it features this beryllium-beryllium bond, and each of these beryllium's atoms is actually only a +1 instead of a +2 charge, which is really unique, and they're already thinking about how to use it in more complex situations. So over here you can see this more even stranger complex, which has got this beryllium-beryllium motif, and then also like a zinc, and these are 2 oxygens that this beryllium is coordinated to. Yeah, we just thought this was pretty cool, and we wanted to include it in the talk. So if anyone has any questions, feel free to let us know. Otherwise, thank you for listening to our talk.